Section 9.7, probability. So, any happening for which there is a result that is uncertain is called an experiment. Oops. Experiment. Now, the possible outcomes of an experiment, the possible results, goodness gracious, got them ahead of myself, are outcomes. And the set of all outcomes in an experiment we call the sample space. And any subcollection of a sample space we're going to call an event. So the probability of that last term, an event. If an event E has n of E ways equally likely outcomes, and its sample space S has n of S equally likely outcomes, the probability of E happening is the probability of E equals the number of ways the event E can happen divided by the number of ways S can happen. That seems more complicated than it really is. So, for example, two coins are tossed. What's the probability that both land up on heads? Now, thinking about our desired event. The only possible outcome that we could get for a desired event, if we were to list them all off, is a heads and a heads. Now, if we're flipping two coins, we have a sample space that would be all of your desired outcomes. And one of them would be a heads and a heads, the one we want. Another one could be, well, what if it's a tails and a tails? Or we could have the first one be a heads and the second one be tails, or maybe the first one's tails and the second one's heads. So in other words, there's 4 total outcomes in our sample space. So the probability of event E happening is just that one outcome that's successful out of the 4. Now there is another way we could approach this problem. The probability of 2 heads in a row would be the probability of heads times the probability of flipping heads, which again is 1/2 times 1/2, which, hey, look at that, that's 1/4. So there's multiple different approaches to this. Now we've got example 2, it says 2 6-sided dice are tossed. Well, it's probably that the total of the 2 dice is 7. So starting off with this one, the sample space isn't going to be too difficult. If you're rolling 2 dice, you have 2 6-sided dice. We're not going to list them all off, but there's 36 total outcomes. Now, to figure out how many different options we have for our desired outcomes, I'm going to encourage you to make a table. And we're going to have dice 1 and dice 2, or die 1 and die 2, I should say. Now, on dice 1, it can be either a roll of 1, a 2, a 3, a 4, a 5, or a 6. Now, in order for them to add up to 7, well, if we roll a 1 for dice 1, the second one has to be a 6. If we roll a 2, the second one has to be a 5. This next one has to be a 4, and a 3, and a 2, and a 1. In other words, there's a total of 6 desired outcomes. So, to do the, the probability of a sum of 7, we're going to do 6 of our desired outcomes out of 36. And of course, we can reduce that to 1 out of 6. So there's a 1 out of 6 chance if you roll 2 dice that you roll a 7. If you've ever played the game Settlers of Catan, or now it's just called Catan, that 7 plays a prominent role because of how likely it is to happen. It's the most common outcome. For example 3, we have a class is given a list of 20 study problems from which 10 will be on an upcoming exam. Now, if a student knows how to solve 17 of the problems, find the probability that the student will be able to correctly guess or correctly answer all 10 of the ones that are chosen on the exam. So our number of desired outcomes. So in other words, the number of 10 questions that, or the number of ways we can choose 10 questions that all of them will be known by the student. Now, in that student's sample space, they have, 17 total questions they feel good about. And we're doing a combination because we don't really care what order the questions come in. So we're hoping that we're going to get 10 out of the 17 that they know. So we're going to have 17 factorial over 7 factorial times 10 factorial. Now I'm going to do this by hand, or actually scratch that. Let's just type that into a calculator. 17 factorial over 7 factorial times 10 factorial is 19,448. Now our sample space is essentially what options the teacher, maybe me, maybe somebody else, could choose from. Well, they've got 20 options and they're going to choose 10 of them. So it's going to be the same setup. We got 20 factorial over, well, 20 minus 10. I don't know why I skipped this in the previous one. Factorial times 10 factorial, which simply put is 20 factorial over 10 factorial times 10 factorial. You can go through that, do it by hand, cancel out as much stuff as you want, but in the end you end up with 184,756 total different ways. So there are a lot of different outcomes that are positive for the student. So like there's 10 problems, if they know 17 of them, there's a lot of chances, but there's also a lot of total options. So the probability that they know all 10 will be the 19,448 out of the 184,756 total different versions of the test they can make. Now, this actually reduces really, really nicely. I wouldn't expect you to identify this off the top of your head, but it ends up reducing to 2 out of 19. They have a 2 out of 19 chance that they're going to know all 10 of the questions.